am going to start the recording and say happy Thursday, happy snow day before Spring Break, Iowa. Coming to you live from Lisa's basement, as usual, on such days. Maybe after spring break we won't have any more snow days. Wouldn't that be nice? I don't want to get my hopes up, though, because I know how this stuff goes. So what we have on tap for today, then, is talking some more about count outcomes. So what's the deal with counts? What are the things that we need to be concerned about when we're trying to model counts as opposed to normally distributed kinds of stuff? Can't go below 0. Yep. We can't have a negative count. 0 is the lowest that it can theoretically be. So how do we fix that problem? Yep, link function. The log link function is what tends to be used. You may see an inverse function or other kinds used with certain types of distributions, but log is pretty much universal for counts. What about the conditional distribution? If it's not normal, what could it be? Poisson? Yep, Poisson family is one option. What's the deal with Poisson? How many parameters does it have? Just one, and that's the problem. Poisson distribution says the predicted mean is supposed to be the same as the predicted variance. So it's a non-constant variance, is where we ended up last time talking about that idea. So if I have a predicted count of 3, the variance around it is 3. If my predicted count is 2, the variance around it is 2. So the variance around it stretches and shrinks as a function of the mean, but that one-to-one correspondence usually does not work for count data. So the idea that you might have a different amount of variance than what the Poisson expects is known as dispersion as a problem. You can have under dispersion or you can have over dispersion. Under means there's too little variance and over means there's too much. Usually we're in the too much category. So if we are in the too much category, what's an alternative to Poisson that we can use? Two-word phrase. First word starts with an N. NG, close. NB, yep. One spot off on the keyboard. Negative binomial. A negative binomial is something you may have seen for its intended purpose, which is the number of trials it takes until something happens. So it's like the opposite of binomial, which is the number of successes out of trials. Negative binomial is like how long you have to do something before you hit a certain result. But at some point, someone figured out how to hack that to turn it into something that we can use with count data instead. So the parameterization, when it's used in a binomial way, is very different. It's very difficult to go across the two in my experience. But the negative binomial, when used for counts, has one extra piece to it. I call it the stretchy factor. I use K in my notation. It's called different things across software, but the idea is that it allows the variance to exceed the mean, and it's by a quadratic function. So then it can grow much more readily. And that was what we were going to start looking at last time, as I recall, right? That sound about right? We looked at Poisson, and we were going to look at negative binomial in our little example. So do you want to look back at this here? Remember the story of the day? Example 3 here. Here's the marginal distribution of y here on page 3. So this is the outcome that we're trying to predict. It is the number of aggressive verbalizations during an experiment that was designed to make people angry or frustrated. And people were assigned to 3 different conditions, either a control condition where they were given no instructions about how to process that information, a cognitive reappraisal, which was described last time as check yourself before you wreck yourself, or try to reframe the situation into something that is less terrible. And then suppression, which was just stuff it down and don't think about it. And suppression is not good for you, apparently. And the question was, does this manipulation work differently as a function of whether somebody has a history of inter-partner violence, IPV for short? So we have a moderation type of model that we're fitting for this example. This histogram by condition, I feel like, is a useful descriptor of what's happening. You can see that in some conditions, there's a lot lower variability and a lower mean. So particularly down here, there's only answers of 1 or 2, versus in some of the other conditions, the count goes up much higher. So not only do we have different means across conditions, but we have different amounts of variability. So we need some kind of non-constant variance model to address this. And we can see to what extent Poisson and negative binomial or some other options will do a good enough job. So we looked at, let's see, we did the normal model. So here's my linear predictor just to remind you what the model is that we're going to fit in every instance. So we have a main effect of interpartner violence, main effects of group, for none is the reference group. And we have each other group, cognitive reappraisal or suppression versus none for the dummy codes. And then we have the two-way interaction between those two. So in this idea, it's one idea of group by IPV, but it takes 2 slopes to differentiate the 3 groups. Likewise, it takes 2 slopes to differentiate the interaction term of group by IPV, and only 1 slope for IPV because it's a binary variable. So we looked at, let's see, the normal model last time. And so this is stata output, for instance, describing just if we fit the ANOVA that the student had intended to do, what would happen. And we end up with a significance test for the joint interaction slopes that was just outside of significance and quite disappointing. That's not a reason not to trust the model, however. A better reason not to trust the model is taken into account when we look at the predicted outcomes for each condition. So for instance, here's some R code that has the predicted cell means. And this thing that I noted out here in the confidence interval is that that condition has a predicted mean confidence interval that goes outside of bounds. So it's extending a predicted count from negative 1.3, which cannot happen. So that's an indicator that we probably need to think about a different model. The residuals then also indicated that the idea of a normal conditional distribution is not going to be a good fit, not just in the shape. So the idea that the distribution doesn't match the bell curve that we're expecting it to, but more important, the idea of heterogeneity of variance. So it looks like the residuals, as the predicted count increases, that's what linear predictor means here. As the predicted count increases, the residuals are more and more spread out, differentially spread out at the higher counts, or at least the middle counts here. So we need a model that anticipates that the residuals are going to have more variability as the count gets higher and higher. So that's what count models are designed to do. Did we look at Poisson? I can't remember if we got this far.
Oh.
We did not? Okay, good. Then I didn't just blank out and like completely forget what I was talking about on Tuesday, which sometimes happens. So we have Poisson to do. So we will, and because the output looks different enough across packages, I have it in here twice. So I apologize for the redundancy, but I know there's a good chunk of people who use each of the programs, and I want to make sure that I can give them the help that they need to be able to use their program of choice. So we are using in Stata to start with here as usual. We have the GLM, which is kind of like a generic general linear models function. It requires you to specify which flavor of general linear model that you want. So the same linear predictor is what we had as before in the normal model. I'm asking it to use maximum likelihood to estimate it. That is the default for certain models, but not for all of them. So I wrote it in here just to make sure. And link log. What do you think that does? Throwing a softball question to get us started here. What do you think I'm telling it to do?
Select the link function.
Yeah, what link function would you like? Yeah, I want the log link. So it's not taking a log of the data. So this is one point of confusion, that if I were to do a log transformation of this data, I would not get the same result. What it is a log transformation of is the conditional mean to be predicted by the model. That's what I'm asking it to do. I would not get the same mean if I logged each individual variable and then took the mean of those logs. The log of the mean is not the mean of the logs. So we have a link function that turns the predicted outcome by this set of predictors, the linear predictor as it's called. It converts that predicted outcome into something that's continuous in both directions on the log scale. When you back translate it into expected counts, though, those expected counts stay above 0 as they should. Family is Poisson. That's going to be your conditional distribution. So Poisson is the built-in option for that. And no log just shuts off some of the output that we don't need to keep it from becoming too voluminous. So there's a new piece of output that we have not seen yet this semester that I'm going to draw your attention to right here. This thing. This is what's known as your Pearson chi-square over degrees of freedom index of distribution fit. We talked about this a little bit last time in some of the slides. The idea is that this is formed as a ratio. It is the average squared deviation from the mean for each individual divided by the standard deviation that is supposed to be there according to the model. So basically it's a ratio of like how much variance is in the residuals in the data versus how much variance does the model think should be there. And in Poisson, it thinks that each predicted mean should have the same amount of variance around it. Like if I have a predicted count of 2, the variance is 2. If I have a count of 3, the variance is 3. So the fact that this ratio is not 1 is telling us that the Poisson is not going to fit. The number here of 4.7 roughly is telling us that there's like 4.7 times as much variability in the data as what the model would predict. So this is my indication that Poisson, even though it's probably more realistic than a normal distribution, is still not a good enough fit yet. These pieces of output then are confirming what you have asked for with respect to the link function. So it's saying, what is my variance function? It's Poisson. What is my link function? It's the log of mu. So it's reminding you what you asked it to do. These AIC and BIC values are different than usual. I'm not even sure what they mean, so we're not going to pay attention to those. I'm not looking at AIC and BIC for this handout. Here's my output. What scale are these coefficients in? We have small numbers, negative numbers. These are in logs. These are log counts. So in the same way that in the last units we had to say this is the logit of the probability of the whatever, this is the log of the expected count for my reference group, which is somebody without a history of IPV who was assigned to the control group for the emotional regulation condition. So they have a log expected count of 0.999. I don't know what that is off the top of my head. You can interpret the direction of these coefficients in the same way. So for instance, the main effective IPV here is in the none group. The expected log count goes up by 0.11 if you're in the violence group instead of the not violence group, and that is not significant. You can say that the expected count of aggressive verbalizations in the no violence group is lower by 1 or 0.14 in the alternative groups. So you can, even though these are in logs, you can look at the direction and say this is a positive slope, this is a negative slope. Question in the chat, what is a usual AIC or BIC? So in most of the time across different types of statistical models, AIC and BIC are a transformation of -2 log likelihood, where AIC is -2 log likelihood plus 2 times the number of parameters in the model. BIC is -2 log likelihood plus the log of n times the number of parameters in the model, I believe. And those basically tell you whether making your model more complicated translates into a good enough improvement in fit. So it adjusts, it's not just the fit of the model, but it's the fit like relative to how complicated it is. So it's one way that people look at those statistics in addition to -2 log likelihood changes for nested models to decide whether or not adding extra parameters is worth it. These ones are not of that kind. They're on some other scale that I have never seen before. So I just have a note that we would not want to use these two values as if they were a traditional AIC and BIC because they're reflecting something else. So we have the two interaction terms here. I want to draw your attention to the p-values that go with them. Do you remember what happened last time in the normal model? If you say no, that's honest. I appreciate that. I figured folks would say no, so I actually have a comparison. Let me scroll for a few minutes here. Here's what happened. How's that? So these are the simple slopes for the difference of IPV per condition, the condition differences per IPV, and then the interaction contrast. So all of these things came out of LinComs in Stata or GLHT commands in R. And I have the results from using an identity link normal distribution versus a log link and a Poisson distribution. So when I say identity link and normal distribution, what would a normal person say that is? Like in not generalized modeling terms, what would that be called if I have an identity link and a normal conditional distribution? Identity link is times 1. Yep. It can be estimated using least squares. Yes, it can. Yeah, this is a general linear model or an ANOVA. So that's what the reference columns here, this is if you just ignored the fact that this is a count and you fit an ANOVA model. That's what an identity link with a normal conditional distribution is. So I want you to recognize the pieces that go into the names that you're familiar with so that you can customize those pieces as you need to do a different type of analysis. So I'm swapping out the identity link with the log link. That's why these estimates are very different. So 0.33, for instance, translates into 0.11 because these are differences in log count, whereas the identity link is differences in the original count. So the standard errors are different as a function of the differences in scale, as well as a difference because we're using a Poisson distribution rather than a normal. But I want to draw your attention to is the last column, the conclusions that we would draw. In the ANOVA model, we had 2 of the interaction contrasts, so the last 3 rows here. 2 of them were non-significant and the third was significant. Now it looks like everything is significant. So if we looked at the output from the log link with the Poisson, we would come to a very different set of conclusions about how significant these effects are. The question is, which ones are more believable? And the answer so far is neither of them. The normal distribution is not really plausible because it expects it to be symmetric, it expects the outcome to be continuous, and to have a constant variance, and we know that that's not happening here. By the same token, Poisson could be more relevant, but in this particular data set, there's way too much variance relative to what the Poisson expects. That we learned, coming back up to the Stata output, with this Pearson chi-square statistic here. So I'm not yet at the point where I trust either of these pieces of information. But you do come to a very different set of conclusions based on what type of model you fit, even if the linear predictor is exactly the same. So continuing an informal comparison, the multivariate Wald test, just for the overall model and the extent to which it predicts this outcome. The chi-square is 111 from the Poisson model. It was only 28 from the normal model. Likewise, the chi-square for the 2 degree of freedom interaction term is 20 in the Poisson model, and it was 5 before. So very different test statistics with respect to whether or not there are differences in slopes across these groups. In Stata, if I want predicted outcomes, I have to be specific as to what scale I want the predicted outcomes in. So these margins commands right here, if I have the option predict XB, that is not a default. Predict XB means make me a predicted outcome in the scale of the model, in the log scale in this case. So I would get a predicted log count for each of these different ranges of my predictor variables. The expected count, so if I unlog it, exponentiate it, then that is given to us by the margins without that option. So the default in Stata is to give you predicted outcomes in the original data scale of expected count rather than the model scale of log count. But these numbers are not going to translate into anything in your estimates table, which are in logs instead. If you want effect sizes, we have the exact same type of effect size in count models as we did in categorical data. It's essentially an odds ratio, but they don't call it that. If you take your slopes and you e to the slope, you exponentiate your slope, you unlog them. That is done with this option called e-form right here. And so then the result of that is interpreted in the same way as an odds ratio. One corresponds to a slope of 0. A positive odds ratio above, or positive slope corresponds to an odds ratio greater than 1. Negative slope corresponds to an odds ratio between 0 and 1. So it's e-form if you want the odds ratio type things to come out of the model. In LINCOM statements, if you want those to be exponentiated, it's an option that is IRR, incident rate risk rate ratio, something like that. I forget what the R's are in that case, but the code online has examples of what that would look like. I didn't print it here since they're so voluminous. Okay, Stata folks, any questions about any of that from the Poisson model?
Sorry, I have a question still related to that AIC and BIC. Why it is unusual here?
Honestly, I don't know. This is the only time that I can remember seeing it. And it's so different that I think in the Stata output, there's actually a hyperlink on it that you can click on and it takes you to a page that explains like what they are.
Okay.
Yeah, I
But
honestly don't know.
then how you know it's unusual because it's like so weird, looks so weird.
If you ask for, so there's an SStat IC command that I usually use to get AIC and BIC printed.
Mm-hmm.
If you ask for that, those values are completely different than what is shown in this section.
Oh.
I usually ask for that. I decided not to in this case because there was already a lot of output to go through. But yeah, these are not the usual kind because they don't match what you get out of SStat IC and they don't match what you would compute yourself based on -2 log likelihood.
Okay, I see. Thank you.
Sure. Other Stata questions before we show the R version of this? All right, let me know if you change your mind. Happy to answer questions later on as needed. So folks using R, you have to do a little more work. Sorry. story of our lives, right? So R does not, in its generalized models, spit out the Pearson chi-square over degree of freedom statistic, but you can make it. The question is, what do you want to use for your degrees of freedom? So the first thing that I had to do in order to fit these models is to generate a piece of information to be used in those formulas. So I am saving 2 new variables to my R environment. I'm calling them DDFN and DDFK. So I am putting in the sample size because that's one way that people will compute this statistic is to use Pearson chi-square over the number of observations as your fit index. What Stata does and what SAS does sometimes is subtract off the number of fixed effects, and so it would be a smaller number in this case. So I made both of these so that you could use either one that you wanted. I'm going to use the Stata one so that the output matches across the 2 runs. So I'm creating this variable based on my current sample size. I'm going to use it throughout the rest of the models that are going to be shown here. So to fit a Poisson model, I am using the GLM base R function. So this is not a package. It just comes with R straight up. We did this one for binary prediction. So you've seen this routine before. The key here is this piece to tell it what flavor of generalized linear model you want, where the word family again shows up. So Poisson is the distribution family, and then the link function is the log. We have the same formula as before. So we have the linear predictor here with my 2 interaction terms, and I'm asking it to print results with -2 log likelihood because that is not something that spits out automatically in this particular routine. So here's the same set of coefficients for my linear predictor. These are in logs. So my intercept, for instance, is the expected log count for somebody who's at my reference level of my covariates. The dispersion parameter for the Poisson family taken to be 1. So that's just reminding you that the idea is that you are expecting as much variance. The idea of dispersion corresponds with variance as what the mean predicts. So there's no over dispersion that's part of this model. The -2 times the log likelihood then is this number right here. That's what will go into your homework. As usual, I always ask for -2 log likelihood because it simplifies the likelihood ratio test that would result. And this command right here is how you make yourself a Pearson chi-square over degrees of freedom conditional fit index. What it is doing is going into the output object that we saved, which I called model Poisson. It is asking for the residuals from that model of the type Pearson. And so it has a built-in function that it knows what the formula should be based on which type of generalized linear model you have. I am then squaring the residual for each person and summing across all the people and then dividing by the degrees of freedom, the version that has the sample size minus the number of fixed effects that is used in Stata. So I am manually computing this fit statistic myself based on the information that's been saved out of my analysis. And that number is exactly what I got back out of what Stata does for you automatically, the 4.69 there. So that means that there is basically 4 times as much variance in the data residuals as there should be if the model fit were correct. So this is telling us that Poisson is not a good enough fit. GLHT Wald tests, just for completeness, for whatever reason it wasn't giving me enough digits, and so I put the results of this inside a print function and added the option digit equals 8 to get enough significant digits to be able to, for example, for this to serve for homework. But otherwise the results are the same. The chi-square fit statistics, or not fit, chi-square test statistics are much bigger than they were relative to the normal model. So the results look rosier than before, but they're not necessarily trustable yet. Predictions then. So here's one set of predictions. I am using a function that is called prediction. It's a package called prediction. It's meant to mimic what Stata does with respect to margins. So you can tell it what model you'd like the predictions from. Type equals link. Can you guess what that does? What kind of prediction?
So use the scale to predict in the scale of the link function rather than the actual outcome.
Yep. So this corresponds to model scale. So type equals link is like predict XB in Stata. It means give me the log counts in this case. It would give me the logits or the probits or the logs or whatever your link is, whatever your model scale is in. So these estimates would directly correspond to what you could build yourself with the fixed slopes. I hear my kid running around upstairs. Hope everything's all right. I assume that if he starts bleeding, he'll come bother me. So, we'll find out. I don't have to worry about him raiding the pantry, though. Most small children, they're constantly wanting snack, right? And if you leave them unattended, they'll eat everything. My kid is the opposite. If I didn't intervene, he would die of malnutrition voluntarily. He just will not eat. He's never hungry, according to him. He is hungry, I can tell sometimes, because kids, when they're hungry, sort of power off. They kind of they get all slumpy and okay, it looks like you need a snack. I'm not hungry. And then once you put something in front of him that he eats, which of course is only carbohydrates, then he starts shoveling, biology takes over, and then I don't worry about it. But he's not going to eat if I don't make him. Fun fact about my kid. Yeah, and also Mewtwo is apparently his new favorite Pokemon card, and there is a Mew1 I learned today. Mewtwo is apparently better, so who knew? Yeah, I have a whole new world to learn about the Pokemon vocabulary. I read stories to him at night that are about Pokemon, like book chapter sorts of stories with people in it and Pokemon characters in it. And sometimes he'll correct me in my pronunciation, and I'm like, this is a made-up word. How am I wrong on this? So, anyway, Mew is more benevolent compared to Mewtwo. Okay, well, good to know. I would have thought that it was weaker or something because most of Pokemon is about battling, but good to know that they're teaching human factor skills. Wait till I get to know about halos and trainer gallery cards. Oh yeah, the trainer cards, he just got some for his birthday, so I have to understand all of those rules now forthcoming. Nothing beats a Ceres? Yeah, it's a whole complicated world. But at least it's cards and not electronics. So that's a sort of a win, because he has to read and do some math, you know, all the subtraction once you lose the points and all that. But anywho, speaking of math, link functions. So yeah, we can ask for predicted logs in that scale. So these are the predicted outcomes per category of my model here, my per cell, as I would say, in log count. And then type equals response. That puts it back into the data scale. So then that is the inverse link result of translating a log count into an expected count. And so the predictions there are the same numbers that I've shown you several times now, because the cell means are the cell means regardless. The difference across models is in the inference that we make about whether those cell means are different than each other. The means are the means. Here's the same picture that I showed you before as to what the patterns of the interaction happen to be. It looks like the effect of suppression rather than cognitive reappraisal or the control group is bigger if you have a history of interpersonal violence than if you don't. So that's my take on the interaction term. And the comparison slide that I showed you before. Okay, so recapping where we've been thus far. Normal, I don't have a way to say that it doesn't fit per se, because I don't have a Pearson chi-square statistic that would make sense for that, given that variance is separately estimated. But I know that if the confidence intervals go below 0, that's probably not a good thing. Poisson seems like it would be better, except in this case, there's way more variance in the data than what it predicts. So we're going to go to Poisson's bigger brother, Poisson 2, as it might be called, instead of mu2. It's actually negative binomial 2. There are like 8 kinds of negative binomials, and 2 is the one that people have decided is the one you should use. So negative binomial 2 is the one that has the quadratic over dispersion stretchy factor. So we're going to do that one next as a contender here. In Stata, I'm going to show you the same model using 2 different functions, because each function only gives you part of the information that you need. So in Stata first, we have a function called NBReg, which stands for negative binomial regression, as it states right here. It does give you a likelihood ratio test for the model built in, and it also gives you this thing right here, which is the whole reason I asked for it. This is a likelihood ratio test done for you as to whether this model fits better than Poisson, whether we need the stretchy. Question in our homework, will we need to do the DFN and DFK? You will need to do one of them. Yes, you will have to make that out of R if you want to use R. Stata will do it for you. Yep. But you can use the code that I gave you and just swap out the model that it points to, and everything should still work the same. So the Stata output here, this part is the same as before. This is my linear predictor. Everything is in log counts, the same as before. The new part is this thing, which it calls alpha, for reasons I do not know. This is the K dispersion factor. So this is the multiplier of the mean squared that allows the variance to exceed the mean in a quadratic function. This is the log of it. It gives you both versions for some reason. I don't know why you would need 2 of them. It's basically the same information on 2 different scales. But the question is, do we need a stretchy factor? Because if this were 0, it would simplify to Poisson. So Poisson is nested within negative binomial, and that K is what makes them different. So it is doing a likelihood ratio test for you against the Poisson model as an alternative. The terminology here is a little bit different than what you're used to seeing. It usually says chi-square, and instead it says chi-bar. And the reason it's different is because this is doing what is known as a mixture chi-square test. The problem is that when K is exactly 0, the log likelihood is not defined. So we're testing a parameter that is like on the boundary of the sample space as the null hypothesis, which in statistics means you need to do something a little bit different. So what it's doing is using a combination of two different degrees of freedom for the test of whether this is different than the previous model. It's using 1 for whenever the k factor would be positive, and it's using a degree of freedom 0, meaning no possible options when the k would have been 0 because it can't go negative. So in practice, what this means, long story short, so to speak, is it cuts the p-value in half to do essentially a one-tailed test, because your k can only be positive and it can't be negative, so a one-tailed test idea makes sense. So that's why it's labeled this way, but the test statistic is 300, and by any standard, that would be a significant improvement. So summarizing, the fact that this is wildly significant is telling us that yes, we need a k-Strachey factor. Yes, the variance needs to exceed the mean in a quadratic function, and here is the multiplier of the squared mean that the model came up with, 1.6. I went back to GLM to fit the negative binomial so that I could get the distribution fit done for me. So note the change to the code. I'm still in link of log, but now I'm in family n binomial, and I want it estimated using maximum likelihood. There are other choices for that. The number that it came up with for the Strachey factor, it put in the variance function for me to describe what it's actually doing. So what the model is telling me then is that the predicted variance around a count, like if you have a count of 2, the variance is going to be 2 as a starting point plus 1.6 times 2 squared. If it were a predicted count of 3, it would be 3 plus 1.6 times 3 squared. So it creates this quadratically increasing variance function as the mean increases. The fact that this number is very close to 1 is good news. That means that the amount of variance in the residuals in the data is very close to what it should be according to the model. In other words, this fits. It's not perfect, but it's much, much better than Poisson. Probably not much I could do to get it to be more perfect than this. So it puts the 1.6 up here. It doesn't give you any hypothesis test related to it. You wouldn't even know about it unless you knew to look for it in the output, which is why I've colored it yellow. Try and draw attention to the fact that this number is a piece of output that it's showing in a weird place. So the likelihood ratio test, by the way, here's the math of what it did behind the scenes for me. The first number is the -2 log likelihood from the Poisson model. The second number is the -2 log likelihood from negative binomial. It's always the model that's simpler minus the model that's more complicated. The difference in -2 log likelihood is the 336. So this is another thing that you will get to practice on your homework, doing likelihood ratio tests for the addition of the Strachey factor to make your variance exceed the mean. So now if we look at the results, these are going to be more believable because we know that the distribution that we have for how much variability is left over is a better fit to what the data actually show. So if we contrast it with the previous results, so normal looked like it wasn't as significant as Poisson, our result is somewhere in the middle. So this is kind of like a Goldilocks model. We have too soft, too hard, Goldilocks is in the middle. But I wouldn't make my choice as to which model to report based on how the answers correspond to what I want to happen. That's not what I'm saying. I'm just putting these here as a point of comparison to show how much difference it can make what kind of variance model you have, what kind of distribution you're using. Last piece here in terms of effect size, I'm going about this two ways. One is that I'm going to ask for incident rate ratios, that's what it's called, which are the equivalent of odds ratios from this model. I can do that by adding E-form and then IRR inside this corresponding LinComs. The other thing I'm going to do is get myself an R-square. How do I do that? By working on it from a backwards perspective. So R-square in standard general linear models is possible because there is a single estimated variance that you have without predictors, and you have another one after predictors, and you can look at the change in the amount of variance that you have and compute an R-square for it. That is a direct way to compute it. An indirect way to compute it relies on another definition of R-square. So when I teach those models, I always talk about R-square in two ways. One is the proportion reduction in the variance after you add predictors. But another is to think of it as R, as a correlation. Another way to understand R-square is to think about y hat as what the model predicts, save that predicted outcome to a column in your data set, correlate that predicted outcome with the real one. That correlation is R. If you square R, that's your R-square. So I can do that even though this is a count model and even though I don't have a single estimated variance, because I can compute predicted counts for everybody and correlate them with the real ones. So that's what I did. So in Stata, there's a direct way to do this. Predict is an option that allows you to save columns to your data set for predicted outcomes, residuals, confidence intervals, and stuff like that. So I am creating a new column with this command called predcount. I am then asking for a Pearson correlation between predcount and my actual outcome, aggressive verbalizations. And then I am asking it to square the correlation that it printed. And then there it is. So my R-square is 0.11 for how much variability in aggressive verbalizations my model has accounted for. So you can have a general effect size like this. You can have specific effect sizes as odds ratio type things for your slopes as well. So the best of both worlds. So far so good. Looks like we have something that we might be able to use, negative binomial. All right, questions? Unless it's about Pokemon cards, in which case I'm going to have to call for reinforcements.
Please, can you explain the interpretation of the slopes with respect to the incidence rate issue?
Can you repeat your question? What do you want me to add? What do you want me to do about the IRR things?
Yes, I don't think I get how to interpret those given for each of the slopes.
Gotcha. So the slopes are in log count. If we take the slopes and exponentiate them, we used to call those odds ratios when it was for predicting categorical data because odds was like the unit that we were predicting at that point. We don't have odds anymore, but the same metric of, it's called an IRR, an incident rate ratio is what they call it. It is essentially like an odds ratio in that if you unlog your slopes, so you exponentiate them, then a zero slope corresponds to an IRR of 1. A positive slope is from 1 to positive infinity, and a negative slope is between 0 and 1. So the metric is exactly like an odds ratio, even though it has nothing to do with odds. But it's the same logic of if I unlog the predicted slopes, then I get e to the slope is this effect size unit. Does that help?
Yes, thank you.
Sure. I hadn't seen these very much in practice, but your textbook, Stata textbook, talked about them quite a bit, so I figure you may as well add a column. As with everything else, like reporting the unstandardized results is going to be, I think, the most transparent thing you can do, but there's nothing that stops you from adding a column to the end of your table that has the odds ratio type things as well. So long as they're clearly labeled and your reader knows what you're supposed to be looking at, I think you're good to go on that. Other questions so far?
You said like because we can correlate the predict outcome and the actual outcome, so we get R here. Mm-hmm. But in categorical, we talk about it's hard to compute R, but like I was thinking, but what if you correlate we still have predict outcome and the real outcome. Why can't we correlate them? Is because they are categorical?
Yeah, so the problem with doing this type of computer predicted outcome correlated with the real one in categorical data is that the predicted and actual are still on different scales even after you do the inverse link. So in categorical, what you end up with is a predicted probability of a 1 for, or a predicted probability of each response category in categorical data. Whereas what you have in the data is just a 0 or a 1.
Okay.
So there's a sense in which like the correlation isn't really fair because variables aren't on the same scale. But what people would do to solve that problem is to round. Like they would say, if I have a predicted probability above 0.5, I'm going to call that a 1. And if it's lower than 0.5, I'm going to call that a 0. And then they'll do like a chi-square contingency to look at reliability or like the R-square type of idea. But that's cheating because like 0.5 is a probability and 0.9 is a probability, both round to 1, but those are very different in terms of like the amount of error that would be around them. So I don't like that idea of rounding because I feel like you're missing a lot of the uncertainty that is inherent in the prediction, but the probability metric is not the same metric as the categorical data metric. Whereas these are both counts. Like counts and expected counts are on the same scale. The only difference is that expected counts can be non-integers. Like you can have an expected count of 1.6, even though your actual count can only be like 1, 2, 3, 4, 5, etc.
Yeah, I see. Thank you.
Yeah, so this idea of computing predicted outcomes and correlating them with the real ones to make an R-square translates into more complicated models as well. So like in the longitudinal models that I teach or the multi-level models, I do the same process, even though those models have multiple variance components happening at different levels of analysis. You can get back to something that is how good is the prediction by thinking about it in a correlation metric. All right. Any other questions before we look at R stuff? All right, so here's my negative binomial in R. This is a separate package that I had to find that is MASS, M-A-S-S, all capital letters. And what it does is basically take the GLM function for Poisson and hack it into being a negative binomial model instead. So it's kind of like an add-on feature to the GLM package. So the function itself inside the MASS package is glm.nb, where nb stands for negative binomial. Because this is negative binomial specific as a function, you don't have to tell it that's what family you want. It's already like built in, but you can still tell it what link function you want because there are choices. And so I have link equals log in here for that reason. Note that for whatever reason here, log is not in quotes, whereas it has been in previous people's packages. So just watch for that as you're working on your homework or trying these models on your own. Sometimes options have to be in quotes and sometimes they don't. And it's based on whoever wrote the package and the way they wanted to do it. So it is very idiosyncratic. That's just the way that R works. So the function itself looks like that. The formula is the same as what we've seen for the linear predictor. And just for fun, R gives you the stretchy factor in the reciprocal metric. So this number that it's printing here, and it's calling it theta, is 0.6. 1 over this 0.6 is the 1.7 stretchy factor that we had before, 1.6. Yeah, there we go. So that was one of the first things I did is ask for it to be flipped. Negative binomial theta is, I found that inside our output inside the environment, so I asked for it to be printed. So it is giving you 1 over k instead of k in R, but you can get back and forth. The formula for these models is written sometimes that way instead, and so I think that's where it came from. I had to do the Pearson chi-square stuff myself again, so here's another example of that. So to use this function, the only thing that you would need to change is what model it's pointing to, what the name of your model is, because I'm using the same degree of freedom variable that I already made. And so the result of this, the 1.11, is the same number that Stata spit out for my Pearson chi-square over degrees of freedom fit statistic, where 1 is as good as it gets, and this is very close to 1, so I'm happy with this. I did not find an easy way to do likelihood ratio tests in R because the ANOVA package is looking for the same type of output in both cases, and I had to use different functions within different packages to get these models, Poisson versus negative binomial. So I did it myself. So the likelihood ratio test to determine whether we need the negative binomial, which Stata did for you in the nbreg command. Looks like this. I'm making a new environment variable called divTest. It is -2 times the difference in log likelihood from each of my models. So log like is a function that extracts the log likelihood out of your model. We just have to multiply the difference in those by -2 to turn that into a test statistic. So devTest is my likelihood ratio test statistic for the difference in -2 log likelihood that's being computed for me. Then I need my p-value. So they have another function that I found, which is p chi-square. So I'm plugging in devTest and degree of freedom 1 because I added one stretchy k to my model to make it different than Poisson. And then making sure the p-value is going in the right direction is the lower tail equals false here. And then to compute the mixture version like Stata does, I cut it in half. So then the end result after asking for those three things to be printed, 336 is the difference in -2 log likelihood between models. That is my test statistic for whether negative binomial fits significantly better than Poisson. Here are the two p-values that go with that, and it is 0 to 75 decimal places. So yeah, just decidedly better. And it doesn't matter if I cut it in half or not to do the proper mixture, I'm going to come to the same conclusion either way. Negative binomial definitely fits a lot better than this. And then we have the chi-square results for the multivariate wald test for the model, as well as for the interaction from before. Last but not least, predicted counts. So I saved, using the predict function, I saved a variable called pred count to my data set. So this is the analog to doing so in Stata, where type equals response means make it in the expected count metric. I then used core test to get a correlation, a Pearson correlation in particular, between the predicted count and the real one. I then asked it to square that R and print it, and there it is. So there's my R square for the model, how well my model accounts for my predicted verbalizations. And then when all is said and done here, I've got my three candidate models side by side, made an Excel sheet to show the results easily. So normal distribution in the first column doesn't fit because it doesn't address the idea that variance needs to be heterogeneous. It needs to change as a function of the predicted count. Poisson tried to fix it but didn't introduce enough variance in doing so, which is evident by the fact that these standard errors are way littler and the p-values are way littler. Negative binomial is the one that actually does seem to fit best, and so the results are somewhere in between the two, where Poisson is too optimistic, normal is too pessimistic, and these are the ones that actually fit the data distribution itself. So we do definitely have a significant interaction for two of the contrasts. The third one is not different, the middle one there. So the story had a happy ending because the negative binomial fit well. If it didn't, I would have had to have kept going. So I have two more models to show you, but not quite yet because I haven't described what they are. All right. So new concepts, trying to go back to the forest instead of the trees here. 4 outcomes that are numbers. There is a chance that we can be wrong with respect to what distribution those numbers fit. We couldn't really be wrong with categorical, but we can with counts, we can with amounts of any kind. So the process then is trying to figure out which distribution fits good enough and also which distributions fit relatively better than each other. Because for count models, Poisson is nested with a negative binomial because the k stretchy factor, if it goes to 0, then it becomes Poisson. We can do a likelihood ratio test to decide which of those we prefer. That is a relative fit comparison because it's just, does this one fit better than this other one? It's the Pearson chi-square over degrees of freedom statistic that tells us whether it fits in the first place. So Poisson did not fit. Negative binomial did fit pretty well, and it fits significantly better than Poisson. So all of that has to be sorted out before you can really believe the results of your analysis, because all of those, the variance model directly affects what the standard errors are. What the standard errors are directly affects what the p-values are. So it's like a downstream process that ends in bad inferences if the variance model doesn't fit. There. How are we doing? Cheers. It's just soda, I promise. I saved the wine for after class. Any questions? Crystal clear, or no one's still here? One of the two, right? We'll see how quickly. Wave to me if you're here. There, a few of you are here. There we go. Peer pressure. Everybody wave. Yes, I know the Zoom environment can become tiresome, so I understand. All right. Let me talk a little bit about zero inflation, and then we'll be done for the day. We're running out of time here. So I'm going back to the slides. This is, by the way, also the last question, I think, on your formative assessment, so we do have to talk about it. Otherwise, you won't be able to answer it. So I'm on slide 7 here. So for counts, we have 3 potential problems with respect to zeros. 2 problems with zeros, 1 problem with variance. On slide 7 here, we've tackled this one so far. So when the mean is not the same as the variance, what do we do to model over dispersion? We can fit a negative binomial. There's other choices for under dispersion. For instance, something called generalized Poisson can be used in those cases. So I want to focus on problems 2 and problem 3 here because they work together with respect to what happens to your zeros. So picking up on slide 13 to talk about this. It may be the case that you're predicting a count outcome that doesn't have any zeros. There is a theoretical lower bound of 0, but it may not be observed in your data. So when this might happen, for instance, is if you're working with archival data, where in order to be in the data set, something had to have happened at least once. So let's say that you have something like hospital data, and you're studying, the number of days that someone spent in the hospital. Well, in order to be in the data set, you had to have spent at least 1 day at the hospital. Otherwise, you wouldn't be there. So in that case, your counts would start at 1. Now, you wouldn't think that would be a problem, but it is. Because the Poisson or negative binomial distributions, those things don't work correctly if there isn't zeros as part of the distribution. It's like there's a hole in it that needs to be adjusted. So there's something called zero-altered or zero-truncated distributions for those cases, in which they basically take off the zero expectation and model the count of everything that's left. Hey, buddy. We're talking about zero-altered distributions. I would run away too.
He ran away. He heard that and he was gone.
It's like,
I don't blame him.
Yeah, I know. It's like, no, mommy, please don't make me. And the rest of you are probably jealous, but you could run away too and come back later if you need to.